Hi everyone, my name is Megan Holdt. I'm a postdoc at the University of Cambridge, and together with Nikki White, we've been compiling sedimentary and crustal thickness constraints. So if we go to the next slide. Thanks, Helen. So these crustal and sedimentary thickness constraints fall under the banner of heat source proximity. So I thought what I'd do is start with a few definitions. So if we flip to the next slide. Okay, so first we'll start with depth to Moho. So this is the thickness between the topography and the Moho, where the Moho is defined by a number of controlled source and passive constraints. You may be aware of the work of Mooney et al. 2023 with the ECM grid. And there's also a very new data set out by Stevenson. It was published just 2 days ago, so that's hot off the press. And his work is under the banner of size crust and their individual spot measurements of depth to Moho.
And Simon's in the call, by the way.
Simon's in the call. So the question really is, out of this total depth to Moho, what proportion is sediment and what proportion is crust? And in the context of geothermal, understanding the difference between what is sediment and what is crust is really important, because they both have very different conductivities and will influence the heat flow in different ways. So if we go to the next slide. So my work has really been in helping to better define the depth to the basement. And so that will provide both a robust sedimentary thickness constraint, but also a constraint on the crystalline component of the crust. Next slide, we'll look now at the method that I've been using to constrain sedimentary thickness. Next slide, Helen. Thanks. Let's look first at the input data. The first piece of information that I look to is the Precambrian basement outcrop. And for this, I used the USGS World Geologic Maps, and Garrity and Solar from 2009 have a geologic map that constrains the location of where Precambrian basement is outcropping at the surface. This is a nice constraint because it tells us that we either have no or very little sedimentary thickness. If we go to the next slide. So the next constraint, and one of the most important constraints, are the well data. I have almost 17,000 wells for North America. And these are excellent constraints on total sedimentary thickness, because in each instance, every well is a definitive intersection of the basement. So these, at any location where we have a well, we have a very good constraint on total sedimentary thickness. If we go to the next slide, and if we flick it sort of just between seismic and wells a few times, so we can see where the seismic and wells are, you can see that in areas where the basement or the sediment is particularly thick, we have seismic to constrain the total sedimentary thickness. So that's in the onshore Gulf of Mexico and also in the Appalachian Basin as 2 key areas. And finally, if we look at the final data set, these are regional grids, and these provide important ISOPAC information in areas where we don't have pre-existing data. And so you can see I've included here all of the different regional studies that I've been able to draw upon to sort of extend the grid in areas where we don't have the well and the seismic constraint. So if we go to the next slide. Okay, the next step is really to interpolate between these measurements. So the resolution of the grid is 0.03 degrees. That corresponds to around 3 kilometers. And this is a significant increase in the resolution of pre-existing global grids, which are typically at around 1 degree. And we'll talk a little more on the resolution in a moment. We're using a minimum curvature gridding algorithm, and we're extending out to the continental shelf. But really our focus is very much onshore, because we're focusing on geothermal. And so extending out to the continental shelf is really to ensure that we don't have those gridding artifacts around the coastline. Something else to mention is that the grid is measured relative to topography. Often you'll see sedimentary thickness measured relative to sea level, where you may have some negative and some positive values. In this case, it's relative to topography, so measurements are only ever going to be positive in terms of sedimentary thickness. Okay, so next slide. Okay, and just pairing back the data so you can see some definition in the basins. This is what the sedimentary thickness looks like for North America. So next slide. Okay, so I thought I'd dive in and share an example from the Appalachian Basin, just to give you a feel for the metadata that we'll be sharing alongside the grid. So let's zoom in now. Thanks, Helen. Okay, so I'll be providing both a grid and also the measurements that constrain that grid. So essentially, if you're an end user of a sedimentary thickness grid, something that's really important to understand is, what controls the overall thickness and what data is underpinning it. Is it wells? Is it seismic? Is it ISOPAC information? Each of which has different levels of uncertainty. So if we go to the next slide. So here we're coloring the data by data type. So the wells are in blue, the seismic is in green, and the ISOPAC information is in red. And so if we were to go to any given well on this image, you would be able to dive in and find more information on the lat, the long, the depth to the basement, the name of the well, the reference, so the original study, and some more information on the uncertainty, and if it's available, information on the basement lithology as well. So next slide. Of course, if you were to deep dive further into the original reference, in this case a study from 2022, you can then gain more information on uncertainties, basement lithology, sedimentary stratigraphy, information on the geothermal gradient, and so on. And so really, you're able to use this metadata to further dive into a basin on a regional scale. Next slide. I also wanted to touch on the resolution of this sedimentary thickness grid. So I mentioned that it's at around the 3 kilometre mark, and existing global grids are at around 1 degree. And so they are significantly a lower resolution. And so what are we gaining when we increase the resolution to this degree? I thought that what we would do is share an example from the basin and range, and also from a region encompassing the Permian, Anadarko, and Gulf of Mexico basins. So if we go to the next slide, and we can zoom in on those two basins. So on the left, we've got the Basin and Range by Shah and Boyd from 2018. So they actually are able to better define the thin sedimentary basins using gravity. And on the right-hand side is our grid of the Permian, Anadarko, and as we move to the south, the Gulf of Mexico basins, defined primarily by well and seismic data and some ISOPAC information as well. So here we're at a resolution of 0.03, and if we go to the next slide, you'll see a decrease in that resolution. So Helen, if I get you to just flick between the two, particularly on the left-hand side in the basin and range, you can see we're really reducing, as we reduce that resolution, we're losing some of the definition in those thin, narrow basins. And maybe on the right-hand side in the Anadarko Basin and so on, we're maybe at between 0.03 and 0.1, not losing too much in terms of information in this case. Now, if we flick to the next step down, half a degree. Yeah, so here at half a degree, we really lose the resolution completely. We don't really gain any sense of there being thin, narrow basins in the basin and range, and we're losing a lot of that lateral variability in this sort of in and around the Permian Basin, Anadarko, and Gulf of Mexico. And finally, let's let's go to the 1 degree, the 1 degree grid. And so this is really the typical resolution on many global grids. And what we're trying to do is develop a grid with a very high resolution on a global scale. And this is just the North America component that you're seeing today. So if we go to the next slide. Yeah, fantastic. Okay, so I really just wanted to highlight the ethos of the approach that we're taking. Firstly, it's very much a data-driven approach. So we're using seismic and wells, and in the absence of those data, we're going out to ISOPAC information from existing regional studies. It will also be quite easy to interrogate as an end user because you'll have both the grid and the underlying data as well. It's potentially also quite buildable. You could potentially add more data quite easily. And also, as with everything that we're producing here alongside Project Innerspace, this work will also be open source. Okay, so if we go to the next slide. Okay, let's now move from sedimentary thickness to crustal thickness. Next slide. Thanks, Helen. So I've been spending quite a lot of time thinking about this sedimentary thickness. We have excellent constraints on the depth to Moho. And so really what we can do is use that depth to Moho constraint and use our sedimentary thickness constraint and subtract that from the total depth to Moho to gain information on the thickness of the crystalline component of the crust. So if we go to the next slide. So this is our sedimentary thickness. If we flick to the next slide. Thanks, Helen. This is the depth to Moho from Mooney. This is the ECM1 grid. And if we go to the next slide, this is the crystalline component of the crust. And you can see, if we think back to where the sedimentary basins existed in our sedimentary thickness grid, some of those areas where we have especially thick sedimentary sequences, that's where we have the particularly thin crystalline crust. And you can see that in the Gulf of Mexico, around the Anadarko basins, in the Appalachian Basin as well. Okay, and we've finished up. I think I've just shown the three outputs. So the first is sedimentary thickness. The second is the depth to Moho from Mooney, but together with Simon, we're exploring whether we could be using the new measurements from Stevenson et al. And the final is the crystalline component of the crust. So I'll leave it there and happy to take any questions.